Hi everyone, so in this video we're going to go ahead and start chapter 13. I'm just going to be going over the first three sections of chapter 13. So chapter 13 is limits, a preview of calculus, and so in the first chapter, or in this first section, 13.1, we're going to learn how to find limits numerically and graphically. Alright, so in this image, we want to see what happens to the value f of x of a function f as the value x approaches the number a. And in this case, we have our a is 2. So we're going to look at what happens as the function approaches a. So in this example, f of 2 is undefined, and our function is x squared minus 4 over x minus 2. So we could look at as x approaches 2 from the left, so we're getting super close to 2, but not quite at 2. So I have 1.99, 1.999, and 1.99999, and you could keep doing that forever. And I have x approaches 2 from the right. So it's not exactly at 2 because 2 is undefined. And as x approaches 2 from the right, those x values are 2.0001 all the way to 2.01. So in both cases, f of x gets closer to 4. So we could see that as x gets closer to 2, the values f of x equals x squared minus 4 over x minus 2 get closer to 4. So in this case, we would say that the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4. So that is just a preview of what a limit is talking about. As x approaches some value, what value should the f of x approach? So let's go ahead and define the definition of a limit. So suppose f is a function defined on some open interval containing the number a. So in our previous example, our a was 2. The function f may or may not be defined at a, so it doesn't have to exist. But the limit notation, the limit as x approaches a of f of x equals L, and this is read, the limit of f of x as x approaches a equals L, meaning that if we get x closer to a on either side of a, but remaining unequal to a, the corresponding values of f of x get closer to L. So in another alternate notation, instead of this other one is f of x, and then you have an arrow L as x arrow a. So in finding the limit of f of x as x approaches a, we don't really consider when x equals a, because f of x doesn't have to be defined when x equals a, so it's just like when we're trying to get really close to a but not quite equal to a, basically, is what the limit is. So the only thing that matters is how f is defined near a, but not necessarily at a. So here we have some images. We have our first graph, f is defined at a, and the limit is at that f of a point, basically. And then in the second graph, we have f of a is this point down here, and then our lit is this right here. So f of a doesn't necessarily equal L. So f of a doesn't equal L, but our limit is over here and not this point. And then here, our f of a doesn't even exist. So we don't have an f of a, but our limit is here. So in all three cases, our limit as x approaches a of f of x equals L. Alright, so now we're going to estimate limits numerically and graphically. So we're going to estimate the limit by taking a table of values, and then we're going to go ahead and check our work with a graph. So I have limit of x approaches 1, x minus 1 over x squared minus 1. So we can see that this function is not defined at 1, because if we were to plug in 1 here, we would get a 0 on the denominator, which is undefined. But that's not what the limit's asking, so we're going to take values close to 1 to see how the function behaves near x equals 1. So I have values of x that are less than 1, and then when I plug that in, they give me my f of x values. And then I have values greater than 1, slowly increasing. And then I have my function f of x and what that gives me. So my x is less than 1. I do like a value that's pretty far away from 1, and then also this one is 0.5 away from 1. And then I get closer and closer. So the more 9s I have, the closer to 1 I get, and then the basically the more 0, 0, 0, 1s kind of thing that I have, the closer I am to 1, because these values are really smaller compared to 0.0001 is smaller than 0.01. And so I get my f of x, and I can see here that it looks like the limit is about 0.5. So from the table, I'm going to make the educated guess that my limit is 0.5. And now I'm going to use a graphing calculator or desmos.com to graph. Okay, so I'm going to go ahead and graph x minus 1 divided by x squared minus 1. And so I have at 1, that's here, it's undefined. But my limit approaches basically here, which is 0.5, as we could see. That's 0.5 around there, and then 0.5 around here. So our limit does match our educated guess that we made of 0.5. Okay, so in this example, I have the limit as t approaches 0 of t squared minus 9 minus 3 over t squared. And so I make my table of values, and I could see here that if I'm doing values like plus or minus 1, plus or minus 0.5, plus or minus 0.1, plus or minus 0.05, because I'm doing values on both sides of the 0, basically. So values that are greater than 0, and then values that are less than 0. And I'm getting about 0.16 on each side. But then when you notice that when I plug in even smaller values, plus or minus 0.0005, I'm getting small values, and then eventually they equal 0. And so in this case, our limit is 1/6. But for some reason, the calculator or the graphing calculator gives us 0. So basically, if you try to see these calculations on your calculator, you might get different values. And eventually you get the value 0 if you make t sufficiently small. So this doesn't mean that the answer is 0 instead of 1/6. The value of the limit is 1/6 in this case. The problem is that the calculator gives false values because our square root of t squared plus 9 is very, very close to 3 when t is small. So basically, when t is small, a calculator's value for the square root of t squared plus 9 is 3.000 to however many digits the calculator is capable of carrying. And so basically, the calculator is just like, it's 3, so 3 minus 3 is 0. So we just need to be careful when we're using the calculator, because sometimes we get inaccurate graphs or inaccurate values because of problems with subtraction. So, but in this case, our limit is 1/6. Okay, so limits that fail to exist. So functions do not necessarily approach a finite value at every point. So sometimes we have a function with a jump discontinuity, a function that oscillates, and then a function with a vertical asymptote. And so in these cases, our limit doesn't exist. So for h of t, I have 0 and 1 if t is less than 0, and then if t is greater than or equal to 0. So I have a jump at x equals 0. So as t approaches 0 from the left, h of t approaches 0. And then as t approaches 0 from the right, h of t approaches 1. So there's no single number that h of t approaches as t approaches 0. So therefore, our limit does not exist. And then for our next example, I have the limit as x approaches 0 of sine of pi over x. So our sine of pi over x is undefined at 0. So we're going to go ahead and evaluate the function for smaller values of x. So I have sine of pi, sine of 3 pi, when I'm plugging in 1, 1/3, 0.1, 1/2, 1/4, and 0.01. And then I get 0. So my guess is that the limit as x approaches 0 of sine of pi over x is 0. However, although f of 1 over n equals sine of n pi equals 0 for any n in the integers, it is also true that f of x equals 1 for infinitely many values as x approaches 0. So maybe if our n or if our x isn't an integer, it'll approach 1. But we can see that it oscillates infinitely around 0. So the dashed lines show the values of sine of pi over x. It's oscillating between 1 and -1 infinitely as x approaches 0. So our limit as x approaches 0 of sine pi over x does not exist. So there are some pitfalls in guessing values of limits as we're guessing the wrong value. It's easy to guess a wrong value. Let me fix my E there. It's easy to guess the wrong value and know when to stop testing values, and sometimes calculators give wrong values. So in our next two sections for 13.3 and 13.2, we'll develop better ways to calculate the limits. Here's another example of a limit that does not exist. So I have a limit as x approaches 0 of 1 over x squared. So I have my values of x on either side of 0, and then what they give me on 1 over x squared. So as I can see, it's just getting closer and closer and closer. They're not getting closer and closer and closer. They're just growing, basically, arbitrarily large. So they're not getting closer to any value. So f of x can be made arbitrarily large by taking x close enough to 0. So f of x doesn't approach a number, so the limit as x approaches 0 of 1 over x squared does not exist. So in this case, we use the limit as x approaches 0 of 1 over x squared equal to infinity to indicate this behavior. So we're not regarding infinity as a number, and it doesn't mean that the limit exists. It just means that the way that the limit does not exist is because we can make 1 over x squared large as we like by taking x close to 0. So it's basically just saying it goes to infinity. And then notice that in this case, when we have our limit as x approaches 0 of 1 over x squared equals infinity, we have that the line x equals 0 is our vertical asymptote. So it's like saying x approaches 0 is our x equals 0. And we could tell that it's a vertical asymptote because that limit goes to infinity. So when a limit of a function goes to infinity, whatever that x approaches a, whatever that a value is, that's going to be our vertical asymptote. Okay, so for one-sided limits, we've kind of looked at this by looking at values greater than or equal to a value. So we have a left-hand limit. So you have the limit as x approaches a, and then the negative sign represents the left hand of f of x equals L. So the left-hand limit of f of x as x approaches a from the left equals L. So as we take x sufficiently close to a, where x is, whoops, let me do it in yellow, where x is less than a, the values of f of x get closer to L. And then for our right-hand limit, we have the limit as x approaches a, and then the plus is for the right of f of x equals L. So the right-hand limit of f of x as x approaches a from the right equals L. So as we take x closer to a, but it remains greater than a, the values of f of x get closer to a. So basically as take x closer to a, but it remains x is greater than a still. Okay, so here I have the different notations. So I have x going to a positive, my x is greater than a, and then my x going to a negative is x less than a, basically. So here's a graphical example. So I have the limit as x approaches a from the left are going to be the values of x that are to the left of a. And then the limit as x approaches a from the right is going to be, so this is like going this way, and then this is, we're following the graph and we're coming right, and then this way we're following the graph and we're coming left. So in comparing two and one-sided limits, this holds. So if x approaches a equals L, that is if and only if basically our left and right side limits exist. So if our left and right hand limits are the same, L, then our limit as x approaches a equals L. And then if our limit of x approaches a equals L, then we have our right and left hand limits are the same. So that's a way we could tell if the limit exists, is if the left and right hand limits agree. Okay, so in this example, we're going to find the following or state that it doesn't exist. So for our first one, we have the limit as x approaches negative 2 from the left. So if we're coming here, this whole graph is f of x. So if I'm coming from the left, I'm coming from this side. And so I have that negative 2, 0 is the red open dot. And so the limit as x approaches negative 2 from the left of f of x, it's going to be 0. So it's going to be this value here. And it's going to be our y value. Okay, so then we have the limit, let me do it in a different color, of x approaches negative 2 from the right side. That's coming from this direction. So if I'm coming here and I'm going whoop, and then negative 2. So it's this blue open dot here. And the point is negative 2, negative 2. And so the limit as x approaches negative 2 from the right is negative 2. And then I have the limit as x approaches negative 2 of f of x. That's going to be the limit, basically. So if we look at our left and right hand limits of negative 2, they don't match. So basically the left and right limits are unequal because negative 2 does not equal 0. So the limit as x approaches negative 2 of f of x does not exist. Okay, so for f of negative 2, this is the blue dot with our coordinate negative 2, negative 1. So this is the actual value of f of negative 2. So f of negative 2 is negative 1. Okay. For our next example, I have 2x squared, 4 minus x, if x is less than 1, and then if x is greater than or equal to 1. So our limit as x approaches 1 from the left, so that's coming from this side, and we see that that is the y value of 2, so that's 2. And the limit as x approaches 1 from the right is coming from this side, and we see that value is 3. But then our limit as x approaches 1 of f of x does not exist because our left and right hand limits don't agree with each other. Okay, I'm going to go ahead and stop the video here, and then we'll continue next time with chapter 13.2. I'll see you then.